Hello my friends, and welcome to KrossUSA channel. Today, we're taking you behind the scenes at some of the world's most innovative production facilities. So grab your coffee and let's dive into these incredible manufacturing processes. Welcome to the fascinating world of precision fasteners. Here at Walter Hassenkamper's facility, we're witnessing something truly remarkable. The birth of screws and bolts that hold our world together, quite literally. What you're seeing here is cold heading technology at its finest. These high-speed, cold forming machines are operating at incredible precision. We're talking tolerances measured in thousandths of an inch. The process begins with premium steel wire, typically grades like 10.9 or 12.9, being fed into the machine at speeds that would make your head spin up to 400 pieces per minute. Watch this beautiful dance of engineering. The wire enters the machine and is immediately cut to precise length by carbide cutting tools. Then comes the magic. The cold heading process. Using tremendous hydraulic pressure, sometimes exceeding 150 tons, the machine literally sculpts the metal without heat, forming the head of the screw in a series of progressive dies. Notice how the material flows like thick honey under that immense pressure. This cold working process actually strengthens the metal by aligning its grain structure. It's like giving the steel a workout that makes it tougher. After forming, each piece travels through an automated threading machine, where precision cutting tools carve those perfect spiral threads. The threading speed here is computer controlled to ensure each thread meets exact specifications. Because when you're making fasteners for aerospace or automotive applications, there's simply no room for error. The final step? Heat treatment in those massive furnaces you see glowing in the background, followed by surface coating for corrosion resistance. It's incredible to think that these tiny components undergo such sophisticated processing. Step into the electrifying world of Tesvicetin, where engineering precision meets electrical innovation. This Czech facility represents the pinnacle of electric machine manufacturing, producing motors and generators that power industries across the globe. Our journey begins at the core preparation station, where silicon steel laminations are being precisely cut using laser cutting technology. These aren't just any cuts. We're looking at tolerances of plus or minus 0.05 millimeters. Each lamination is coated with a special insulating varnish to prevent eddy current losses, which could rob efficiency from the finished motor. Watch as these automated stacking machines build up the stator cores layer by layer. The hydraulic pressing system applies exactly 25 tons of pressure to create a perfectly compact core. The precision here is absolutely critical. Any air gaps or misalignment could cause vibration, heat buildup, or efficiency losses in the final product. Now we move to the winding department. This is where the real magic happens. Those sophisticated CNC winding machines are laying copper wire with mathematical precision. For a typical three-phase motor, we're looking at hundreds of turns per coil, and each turn must be placed with absolute accuracy. The tension control on that copper wire is monitored continuously. Too loose and you get poor performance. Too tight and the wire could break. The insulation process you're witnessing uses VPI vacuum pressure impregnation. The entire stator assembly is placed in a vacuum chamber, then flooded with specially formulated resin under pressure. This eliminates every air pocket and creates a solid insulation system that can withstand thousands of volts and extreme temperatures. Moving to rotor production, those massive lathes are turning steel forgings into perfectly balanced rotating assemblies. The dynamic balancing machine you see there can detect imbalance as small as 0.1 gram centimeters. That's incredibly sensitive, but absolutely necessary for smooth, vibration-free operation. The shaft pressing operation uses hydraulic force exceeding 200 tons to ensure perfect concentricity. Computer monitoring tracks the pressing force continuously. If it deviates even slightly, the system automatically adjusts or stops the process. Final assembly brings everything together in a temperature-controlled, clean room environment. Those precision measuring instruments are checking air gaps to within 0.1 millimeters. The space between rotor and stator is critical for electromagnetic efficiency. The testing phase is equally impressive. Each motor undergoes load testing, insulation testing up to twice its operating voltage, and vibration analysis. The data from every test is recorded and becomes part of the motor's permanent record. Welcome to Gränsfors Brook, where Swedish craftsmanship meets centuries-old tradition. Here in the forests of Sweden, master smiths are creating axes the way it's been done for over 100 years, with fire, steel, and incredible skill. What makes these axes special starts with the steel selection. We're looking at high-carbon steel, typically around 0.7% carbon content, which provides the perfect balance of hardness and toughness. But here's the fascinating part. Each axe head uses two different types of steel welded together. Watch as the smith heats that carbon steel bit to exactly 100 degrees Fahrenheit in the coal forge. At this temperature, the steel glows bright orange and becomes malleable enough to shape. The eye of the axe, that's the socket where the handle fits, is formed using a specialized tool called a mandrel. The smith literally wraps the hot steel around this form, creating that distinctive teardrop shape. Now comes the welding process. And not talking about modern electric welding. This is forge welding, where two pieces of steel are heated to welding temperature and hammered together. The carbon steel cutting edge is being welded to a softer iron body. This creates an axe that's incredibly sharp but won't shatter under heavy use. The power hammer you hear pounding away delivers precisely controlled blows. Each strike shapes the metal, while the smith constantly rotates and repositions the piece. Years of experience tell him exactly when the steel is at the right temperature, when to reheat, and how much force to apply. The grinding process uses traditional water-cooled sandstone wheels. Some of these grindstones have been in use for decades. The slow grinding speed prevents overheating that could ruin the steel's temper. Each axe is ground to achieve that perfect convex edge geometry that makes Swedish Axes legendary for their cutting performance. Heat treatment is the final critical step. The cutting edge is heated to 500 degrees Fahrenheit and quenched in oil, then tempered back to achieve the perfect hardness of about 57 HRC. Too hard and it's brittle, too soft and it won't hold an edge. Enter the world of renewable energy manufacturing at Seablade, where engineering meets environmental responsibility. These aren't just turbine blades, they're 150-foot giants that will harness wind power for decades to come. The process begins with precision mold preparation. These massive molds, some weighing over 100 tons, are heated to exactly 80 degrees Celsius and treated with specialized release agents. The surface finish must be absolutely perfect. Any imperfection will transfer to the blade surface and could affect aerodynamic performance. Watch as technicians apply the gel coat. This isn't just for appearance. The specialized polyester resin provides UV protection and weather resistance for 25+ years of outdoor service. The application technique is critical. Too thin, and you get poor protection. Too thick, and you add unnecessary weight to a component where every pound matters. The layup process you're witnessing is a marvel of composite engineering. Those aren't ordinary fabrics being laid down. We're looking at specially woven glass fiber reinforcements, some incorporating carbon fiber for additional strength and stiffness. Each layer is oriented at precise angles to handle the complex loading forces these blades will experience. The resin infusion system is computer-controlled to ensure complete saturation. Vacuum pumps create negative pressure, while specialized pumps inject epoxy resin at exactly the right viscosity and temperature. The entire blade must be infused in one continuous process. Any delays could result in weak spots that could lead to catastrophic failure. Curing takes place in massive autoclaves, essentially giant ovens that can heat-treat the entire blade assembly. Temperature and pressure are controlled to within tight tolerances throughout the 8-hour cure cycle. We're talking about 120 degrees Celsius at 3 bars pressure, maintained uniformly across a component that's longer than a football field. The precision machining of the root section uses specialized 5-axis CNC equipment. Those bolt holes must be positioned with astronomical accuracy. We're talking tolerances measured in hundredths of millimeters. When this blade is installed 300 feet in the air, there's no room for adjustment errors. Welcome to Starco's steel wheel manufacturing facility, where raw steel becomes the foundation of mobility. These aren't just wheels, they're precision-engineered components that must withstand enormous stresses while maintaining perfect balance and durability. The process starts with premium steel disc blanks, typically made from high-strength, low-alloy steel. These blanks arrive pre-cut by laser or plasma cutting to exact specifications. What you're seeing here is cold-forming technology. The steel is shaped without heat, using tremendous hydraulic pressure. That massive stamping press generates over 2,000 tons of force. In a single stroke, it transforms a flat steel disc into a complex 3-dimensional wheel shape. The tooling precision here is extraordinary. The dies are manufactured to tolerances measured in thousandths of an inch and are capable of millions of forming cycles. The rim welding process uses specialized resistance welding equipment. The wheel rim and center section are joined using precisely controlled electrical current that creates a molecular bond between the steel surfaces. This weld joint must be stronger than the base material itself. Quality control testing actually proves this by testing sample welds to destruction. Watch the automated balancing operation. Each wheel is spun at high speed while sensors detect any weight imbalances. Computer-controlled drilling removes small amounts of material to achieve perfect balance. We're talking about tolerances of just a few grams on a component weighing 40+ pounds. The powder coating process provides both protection and appearance. The wheels are electrically charged while powder particles are sprayed on. Electrostatic attraction ensures complete, uniform coverage. The curing oven operates at exactly 200 degrees Celsius for 15 minutes, creating a finish that's more durable than liquid paint and environmentally friendly. Final inspection includes dimensional checking, load testing, and visual inspection. Each wheel must meet stringent automotive industry standards before it earns its certification stamp. Step into Nide Group's state-of-the-art facility, where the heart of every washing machine motor is born. These 3-phase stators represent the perfect marriage of electromagnetic theory and manufacturing excellence. Our journey begins at the lamination preparation station. Those aren't just steel sheets. They're specially formulated silicon steel with magnetic properties optimized for electric motor applications. The silicon content reduces core losses, while the grain-oriented structure maximizes magnetic flux density. Watch this incredible punching operation. This high-speed progressive die system is stamping out laminations at over 500 pieces per minute. Each lamination has 24 precisely shaped slots that will hold the copper windings. The accuracy here is phenomenal. Slot dimensions are held to plus or minus 0.025 millimeters tolerance because any variation affects the motor's electrical characteristics. The automated stacking system builds the stator core layer by layer. Notice how every lamination is rotated slightly? This technique, called skewing, reduces magnetic noise and vibration in the finished motor. The hydraulic pressing system applies exactly 50 tons of pressure to create a solid, compact core assembly. Now we enter the winding department, the crown jewel of stator manufacturing. These CNC winding machines are engineering marvels. They're inserting preformed copper coils into those 24 slots with robotic precision. Each coil contains exactly 85 turns of copper magnet wire, and the wire tension is monitored continuously to prevent damage. The wire itself is specially engineered. It's copper with a polyester amide insulation system rated for 180 degrees Celsius operation. The cross-sectional area is calculated to carry the motor's rated current with minimal losses while fitting perfectly in the available slot space. Watch the connection process where coil ends are joined to form the three-phase winding pattern. This isn't random. It's a carefully engineered sequence that creates the rotating magnetic field necessary for motor operation. Each connection is resistance welded using computer-controlled equipment that monitors weld quality in real time. The insulation system is critical for motor reliability. That VPI vacuum pressure impregnation process removes every air bubble and fills every void with specially formulated varnish. The vacuum chamber operates at less than 1 torr pressure, that's nearly a perfect vacuum, before flooding with insulating resin under 6 bars pressure. The baking process cures the insulation at exactly 155 degrees Celsius for 8 hours. Temperature is monitored at multiple points to ensure uniform curing throughout the assembly. This creates an insulation system capable of withstanding thousands of volts during testing and years of reliable service. Quality control is exhaustive. Every stator undergoes HIPAT testing at 500 volts, surge testing to verify winding integrity, and impedance testing to ensure proper electrical characteristics. The data from every test becomes part of the stator's permanent quality record. Welcome to Rico's impressive facility in India, where cooling comfort is manufactured with remarkable precision and efficiency. This isn't just fan assembly, it's a masterclass in optimized production flow and quality engineering. The process begins with aluminum die casting for the fan motor housing. That massive die casting machine injects molten aluminum at 650 degrees Celsius under 800 tons of pressure into precision steel molds. The aluminum alloy used here is specially formulated for electrical applications. It provides excellent heat dissipation while maintaining the strength needed for continuous operation. Watch the precision machining of the motor housing. Those CNC machines are creating bearing seats accurate to within 0.01 millimeters. The surface finish is critical too. It affects heat transfer and bearing life. The cutting speeds and feeds are optimized for aluminum's unique machining characteristics. The stator winding operation uses semi-automatic equipment, perfectly suited for the production volume. Each stator gets exactly 240 turns of copper magnet wire per pole, wound with precise tension control. The wire gauge is calculated to handle the motor's current, while minimizing energy losses. Blade manufacturing showcases India's expertise in sheet metal forming. Those progressive dies transform flat steel sheets into aerodynamically optimized blade profiles in multiple forming operations. The blade angle is precisely controlled. Even small variations could affect airflow and noise levels. The balancing operation is fascinating to watch. Each blade set is assembled and tested on dynamic balancing equipment. Small weights are added or removed to ensure smooth, vibration-free operation. The tolerance here is remarkably tight, less than 2 grams of imbalance on the entire blade assembly. Motor assembly brings together precision-manufactured components with skilled hand assembly. The rotor stack uses laminations punched from high-grade silicon steel, while the commutator segments are made from high-conductivity copper. Each brush spring is adjusted to provide exactly the right contact pressure for optimal performance and longevity. The quality control process includes no-load testing to verify proper rotation and current draw, followed by loaded testing to simulate real-world operating conditions. Noise level testing ensures every fan meets strict acoustic standards, critical for bedroom and living room applications. The final inspection includes a complete functional test, where each fan operates for 30 minutes under full load. Temperature rise, vibration levels, and electrical parameters are all verified to meet specifications before the fan earns its quality certification. From raw materials to finished product, Ricoh's process demonstrates how traditional manufacturing excellence combines with modern quality systems to produce ceiling fans that provide reliable comfort for millions of homes across India and beyond.